Welcome to solverfy.
College athletes apparently don't have much interest in the academic side of their college experience, and we are looking to test if we can fix that by monitoring attendance. So, part one, we want a two-tailed test to look for a significant change. We start by stating the hypotheses. The null hypothesis represents no change, no difference. We are looking at the differences in lateness. So if there's no change, the mean of the differences would just be 0. If there is a change, then the mean of the differences would no longer be 0. If there's an improvement, then we're looking at a decrease, so it would be above 0. If it makes it worse, then it will be below 0, meaning an increase in lateness. Our sample size is 16. Our sample mean is 21, and this is the mean difference. The sum of squares is 2,940. Now, to perform a hypothesis test, you start by assuming the null hypothesis is true. So we pretend the mean of differences is 0. The monitoring of the attendance does not make a difference. If we were to take every sample of size 16, take the means, plot them out, hopefully we would see something approximately normal. We have a really small sample here, so it's not ideal, but we do have to use this in order to get the t-value. So the sample means would follow a normal distribution, mean same as the population mean, standard deviation sigma over root n. I don't know what sigma is. We have not been given the population standard deviation, so we're going to have to use the sample standard deviation, which we haven't been given either, but I can find it. To get the sample standard deviation, take the sum of squares, divide by n-1, square root. n-1 because it's a sample standard deviation. So 2,940 over 15 is 196. The square root of that is 14. Now, because sigma is unknown, it's going to be a t-test. I'm going to find the critical values and I'm going to find the test statistic. So it's a two-tailed test, meaning that we have two rejection regions. I care if the difference is very negative or very positive. So you have two rejection regions. They are going to split alpha between them. Here, alpha is 1%. So I want to know when my sample mean would fall on this curve. If it falls here, I would say it's not 0, but this wasn't unlikely. It is plausible that our sample data belongs to this curve, and we just happened to get something this high. But if our sample mean is in a rejection region, we say, okay, if the null hypothesis is true, this result is really unlikely. Therefore, I don't think the null hypothesis is true. An alpha of 1% tells me that if something is 1% or less likely, then I reject the null hypothesis. So two tails, they split alpha between them, so each tail is 0.5%, and we're using t. So we also need degrees of freedom, which is just n-1. So you want t sub 0.005 with 15 degrees of freedom. You can get that from a t-value table or from software or your calculator. It's plus minus 2.947 to 3 decimal places. Now for the test statistic, basically the z-score of the sample mean. Again, we just call it t because we're looking at a t distribution. To find a z-score, you take the raw value, you subtract the mean, you divide by the standard deviation, or what we think the standard deviation is. So here we have 21 minus 0 divided by 14 over root 16, which is 6. That is very extreme. That is definitely in the rejection region here. We reject null hypothesis. We found a significant difference. Because our test statistic is more extreme than the critical values. Part 2, we want a confidence interval for the population mean. Now the formula here is x bar plus minus ts over root n. So the S over root n is our estimate of the standard deviation here. This time t is telling us how many standard deviations in either direction we have to go to get this interval of 95%. So this time each tail is only 2.5%. We've changed it to 95% confidence, meaning alpha is 0.05. We still have 15 degrees of freedom. So this time t is plus minus 2.131. And the interval looks like 21 plus minus, let me calculate the error. So we've got 2.131 multiplied by 14 over root 16 is 7.46. If I subtract that away from the point estimate, I get the lower bound, 13.54. Add it on, I get the upper bound, 28.46. So we are 95% confident that the mean change in attendance is in that interval.